Welcome to The Explainer, where we break down big topics into clear, understandable ideas. And today, we are going to jump into two of the most powerful and honestly most important concepts in all of mathematics, exponential and logarithmic functions. So, let's start with a bit of a puzzle. What could a viral cat video possibly have in common with your savings account? I mean, they seem like totally different worlds, right? Well, the answer is all about how they grow. You see, both of them can experience this incredible, explosive kind of growth. It's that thing where something starts out really slow, almost unnoticeable, and then all of a sudden it just takes off like a rocket. This isn't just adding a little bit at a time. It's something way more dramatic. To really get a handle on this, let's look at a classic example from our source material, population growth. Think about it. The increase in population each year isn't a fixed number. It depends on how many people are already there. The more people you have, the more the population can grow. So it's not adding, it's multiplying. And that multiplying effect is what causes this growth to accelerate and just surge.
Okay, so how do we even begin to describe this kind of runaway change with math? We need a special language, a tool built specifically for this kind of rapid, accelerating growth.
And that tool, my friends, is the exponential function. The whole secret, the magic ingredient is right there in the setup. The variable, the thing that changes, like time, isn't down on the main level, it's up in the exponent. And that one little detail is the source of all its incredible power.
Now, it's super easy to get this mixed up with something that looks similar, the power function, like x squared. We all learned that one in school. But see the difference? In a power function, the variable is the base. In an exponential function, the variable is the exponent. And that changes everything. One is a rocket ship, and the other, by comparison, is a bicycle.
And here you can see that difference in action. It's so clear on this graph. Look at the blue line, the power function. It's climbing, sure, nice and steady. But then look at the red exponential function. It kind of hangs out at the bottom for a bit, and then, whoosh, it just goes vertical, completely leaving the other function in the dust. That curve, that explosive takeoff, that is the signature of exponential growth. All right, so to really work with these things, you need a toolkit. These are the laws of exponents, pulled straight from our source. Now, don't let the list intimidate you. They're just the basic rules of the road that let us simplify and solve problems. Like that first one, it just says if you're multiplying two terms with the same base, you can just add the exponents together. It's the instruction manual for our new rocket ship.
So this all builds up to a very, very special number. It's a number that seems to be hardwired into the universe, showing up everywhere from the spirals of a galaxy to the interest on your bank account. It's kind of like nature's secret ingredient for growth.
It's called E, and it's an irrational number, which just means its decimals go on forever without repeating. It's about 2.718. The mathematician Leonhard Euler did a lot of work with it, and it turns out to be the absolute perfect base for describing any process that grows continuously without stopping.
And here's why E is so cool, what makes it so unique. When you graph the function e to the power of x, something magical happens. The rate of growth at any single point on that curve, you could call it the slope or its speed, is exactly equal to its value, its height, at that very same point. So when its value is 2, it's growing at a rate of 2. When it's 10, it's growing at a rate of 10. Its growth is perfectly proportional to its size. It's the pure mathematical signature of natural growth.
And we see this in the real world all the time. This example from our source is perfect, continuously compounding interest. What that means is your money isn't just growing once a year or once a month. It's growing constantly, every moment of every day. And the number that makes it possible to calculate that constant growth? You guessed it. It's E.
Okay, but what if we flip this whole problem on its head? What if we know the destination? We know how much money we want, but we need to figure out how long it's going to take to get there.
Yeah, this question is really the key. We're great at calculating growth over a certain amount of time, but how do we solve for the time itself? How do we work backwards when that variable we need is stuck way up there in the exponent?
Well, for that, we need another tool. And that tool is the logarithm. It is the perfect inverse, the other half of the exponential function. A logarithm just answers one simple question. What exponent do I need to get this number? So the log base 2 of 8 is 3. Why? Because 2 to the power of 3 is 8. See? It just undoes the exponent. It's like a what power machine.
And this graph just captures that relationship perfectly. You can see the exponential function e to the x soaring upwards. And you see the natural log, or ln of x, as its perfect mirror image, reflected across that dotted line. They are a perfect pair. One function does, the other undoes. They're truly two sides of the very same coin.
So now that we have this inverse tool, now that we have the logarithm, we can finally put it to work. We can finally solve for that variable when it's trapped up in the exponent. Let's just walk through this example from the source material. We've got 5 to the power of x equals 2. How do we get that x by itself? Easy. We take the natural log of both sides of the equation. Now, here's the cool part. One of those properties of logarithms lets us take that x from the exponent and just bring it down in front. And just like that, with a little division, x is no longer trapped. It's unlocked.
And really, this is why this all matters so much. These aren't just abstract ideas for a math test. They are the language we use to describe our world. As our source puts it, these functions give us the power to model and predict everything from the growth of bacteria to the decay of radioactive materials.
So, now you have this powerful language. You can see both sides of growth, the building up and the figuring out. So my question to you is, what patterns will you start to see in your world now? What will you look at and say, ah, that's exponential? Thanks for joining this explainer.